Hello, my name is Salah and I will present my work today, which is titled Reconfigurable Intelligent Surface Assisted Visible Light Communication for Outdoor Applications. The outline of my presentation would be as follows. I will start with Introduction to Visible Light Communication Systems. Then I will highlight some of the challenges for VLC systems. Then I will talk about reconfigurable intelligent surfaces and discuss some of the outdoor RIS-Assisted Visible Light Communication Systems before concluding my presentation with a simulation study and showing some results. Visible light communication utilizes the light-emitting diode-based luminaries to provide both illumination and communication for users. In such systems, the LED-based luminaries will act as a VLC transmitters, whereas the receivers utilizes photodetectors to receive the optical signals. VLC systems in general faces several challenges that hinder its deployment. Here I will focus on two of them, which is line-of-sight blockage and VLC transmitter-receiver alignment. Due to the physical properties of light, the signal cannot penetrate through obstacle. In order for the system to operate properly, we need a clear line of sight between the VLC transmitter and the VLC receiver. Another challenge we will talk about, which is the alignment between the transmitter and receiver. Due to the limited field of view of the VLC receivers, in order for the system to operate properly, we need the transmitter and receiver to be aligned to each other in order for the VLC receivers to receive the optical signal. One of the viable solutions researchers propose to overcome such challenges is to introduce what we call reconfigurable intelligent surfaces in the communication environment. Now, first of all, if we would like to define these RISs, it's low-cost elements that is able to reconfigure the incident signals to improve the communication performance. Now, starting with the line-of-sight blockage that we just discussed, it will create a non-line-of-sight link between the VLC transmitter and VLC receiver in case there is an obstacle between the VLC transmitter and receiver. The same thing goes with the VLC transmitter receiver alignment. If the transmitter and receiver are not aligned, these RIS elements will work on reconfigure or reflect the signals coming from the VLC transmitters to the VLC receivers. Now, to give you an idea on how these RISs looks like for VLC systems, here I show one of the possible realizations of such RISs, which we call mirror-based RISs, which is a series of small mirrors, each of them connected to a mechanical system that is able to adjust the orientation of the mirror. By adjusting the orientation of the mirror, it will control how the incident beams will be reflected through these RIS elements. The main focus of my work is to show how these RIS arrays can support outdoor VLC systems. Particularly, I will focus on VLC-based UAV networks, VLC-based V2V networks, and VLC outdoor to indoor communications via the RISs. I will start with VLC-based UAV communication, where in such technology, unmanned aerial vehicles will be equipped with LEDs to act as VLC transmitters, and it would provide illumination and communication for users. Such technology is favored in applications such as search and rescue missions and in hazardous locations to provide both illumination and communication for users. And here we show two examples where the existence of RIS will support the communication. The first one, which is to mitigate line-of-sight blockage. Again, here we show that UAV is supporting several users. However, the line-of-sight link between the UAV and the user is blocked via trees. However, if we have RIS arrays installed in the building surfaces, it will create a non-line-of-sight path between the UAV and the user. Another example is, since the transmitters of these UAVs will be pointing downwards to serve the ground users, inter-UAV communication is not possible via the VLC. However, by having the RIS arrays installed in the building surfaces, it will allow such communication by reflecting the incident beams coming from one UAV towards the other. The second application that I will highlight is how the existence of RIS arrays will support vehicular visible light communication. In such technology, the head and back lights of the vehicles are utilized as VLC transmitters and receivers. And here we discussed two examples, which is mitigate line-of-sight blockage and enable communication between parallel vehicles. For the first one, if we have two vehicles approaching road intersection, obviously the line-of-sight link can be blocked via large buildings. However, by having RIS arrays installed in buildings near to the road intersection, it will create a non-line-of-sight link between the two vehicles approaching road intersection. For the other example is, if we have two vehicles moving parallel to each other, the transmitters and receivers here are not aligned, and such communication is not possible via VLC. However, by having RIS arrays installed on the street lights, it will reflect the signals coming from one vehicle towards the other. On a different dimension, recent developments of these RISs showed that they can be made from transparent materials. In this case, the signal can be refracted through these RIS elements and steered towards specific locations. Given the special properties of these refracting RISs, it motivates the idea of connecting outdoor VLC systems to indoor users. By having some of these refracting RISs installed at the windows of the buildings, it will allow the signals originated from outdoor VLC systems, such as VLC-based UAVs and street lights communication towards inside or indoor users. Now, to highlight the merits of considering RISs in outdoor VLC systems, we carried out a simulation for walkway scenario in an urban area. Here we have some pedestrians are distributed in the scenario, and they receive the signals from VLC transmitters here circled in red, and we have here some RIS arrays to support the communication. Also, to mimic a practical scenario, instead of assuming that the devices held by the users are pointing upward, we assumed random device orientation, where we adapted one of the known models for random device orientation. Now, since we assumed random device orientation, users may experience link outages, which is the probability that the optical signals lies within the reception area of the VLC receivers. Now here we draw a comparison between a system without RISs and a system with RISs. We can see that with the RISs, the outage probability is improved. This is due to the spatial diversity provided by these RIS elements. Also, we can notice that as we increase the number of RIS elements in the scenario, the outage probability will also be decreased, since each combination of VLC transmitter RIS element and VLC receiver will create a new opportunity for the VLC signals to arrive at the VLC receiver. By this, I conclude my presentation. Thank you for your attention.